Hello, everybody. In this video, I'm going to talk about the concept of energy. Okay. Last video, we talked about the concept of work and power. Now I'm going to talk about energy. So let's just imagine with me that I have this marker sitting on the board there, and if I have this brick just right above it, okay, well, there's a chance that the brick might crash it and break it. Okay. If I go higher, right, the chance of breaking the marker had just increased. Right. If I go even higher, right, there is a bigger chance that I might break it. So conceptually speaking, we say, well, the brick has acquired some energy, some form of energy, right? Because now it has, each time you raise it higher, the potential of breaking the marker just increases, right? And that energy that it's got has something to do with me doing work on it to raise it higher and higher, right? So, and I'm working against the force of gravity. I'm pushing the brick up. So it's got to be, this energy has to do somehow with the with gravity. So we call this gravitational potential energy. Now, gravitational, it's understood because we're working against gravity, but potential, it doesn't have to actually do damage on the marker to actually see the energy or feel the energy or sense the energy. But I know that if I drop it, it will definitely cause some damage. So it has the potential of doing something while it's sitting there. Okay. Another type of energy has to do with motion. So if I have these two markers, right, next to each other, and I'm driving a car, right? So, and I'm accelerating, let's say. My speed by the time I get to the black marker is greater. So if I'm driving my car, I'm going at a slow speed by the time I reach the red marker. So the chance of me breaking the marker is greater when I'm at the black marker than it is when I'm at the red marker. So we say here that some work was done by the engine, first of all, to take you from a low speed to a higher speed. And that work, right, basically just gave the brake or the car a greater amount of some other form of energy. Well, this energy has to do with the object, with the motion of the object. It has nothing to do with the elevation, with the position. So this is what we call kinetic energy. Kinetic means moving. And then the other type of energy is the elastic potential energy. And that's when you change the shape of something. So if I take this bow and arrow, or if I take a spring or a rubber band, so if I pull slowly, gently on it, right, I'm doing some work. And you know that the work here varies as the x square. We talked about that in the last video. So if I pull with a little force, well, it causes a little stretch. So there is some energy stored in the bow and arrow. Now, if I pull more, if I double the amount of stretch, I quadruple the work that I did, right? Now I'm storing more and more energy in here. And that's easy. So if you have an arrow here, if you stretch it a little bit and if you fire, right, yeah, you might hit something and cause a little bit of a damage. But if you stretch it more and you let go, you will cause a bigger damage. So this kind of energy has to do with changing the shape of an object. Okay. Now I'm gonna try to derive the formulas for all these types of energies. So let's just take something on a ramp that's initially going at a velocity of VO, and by the time it gets here, it's going at VF, and maybe it's gonna keep going up, all right, on the ramp. This angle here is theta. So I'm gonna take this object when it's halfway here, I'm gonna do a free body diagram. So there is a force acting on it up, right? And then you have your weight, but you also have, I'm just gonna do the components here so I can go quickly. The perpendicular component doesn't do anything. It's the parallel component of the weight that does some work. Okay. So I'm gonna write F net equals MA. So F net is basically the FA minus mg sine theta equals MA. Well, the A, I'm going to do it without having the time. So if you remember the equation in kinematics that has the v squares, that's the one you're going to have to solve for A. We're traveling a distance d from here to here. Okay? All right, so now if I multiply both sides by d and I move the mg sine theta to the other side, let's see what happens. Fa times d equals mg d sine theta. I'm doing like 3 steps in one here. So plus 1/2 m vf square minus v initial square. Okay, well, this F times D, that's basically just the work done by force A. And look what the work done by force A did. It changed after I see that D sine theta is just H, is this height here. Okay, that's done in the last video. The work done by the applied force must have changed my level of energy, right? So this mgh is what we call the gravitational potential energy. I don't know why they call it U, but that's what it is. Okay? The kinetic energy is basically 1/2 mv squared. And you can see that since this started with an initial speed, the work done changed its kinetic energy. It caused a change. Okay? What else? Okay, when it comes to gravitational potential energy, I use this point as the reference. And I would do that all the time. I would pick the lowest point of my trip as the reference. Okay? So for instance, for the marker, going back to the marker, this break here, with respect to the marker, since it's above it, has a positive amount of gravitational potential energy. So that's the mgh. Okay, if it's down here, it has a negative amount. So I'm going to try my best to not work with negative gravitational potential energy, because you're going to see later that it's really the difference in gravitational potential energy that's important. It's not the actual gravitational potential energy itself. It's the difference. And even with kinetic energy. So if I'm going to drop this, it's going to get all the way down to the floor. I'm going to pick the floor as my reference point for the gravitational potential energy. At the ground level, I have 0 gravitational potential energy. Again, it's all about the difference. Okay. Now, so those are the definitions. The other thing I want you to see here, which is also powerful, and I'm going to talk about this in the next video, this Fa minus mg sine theta, that's just the net force. Now, if I multiply both sides by d, I will get 1/2 mvf squared minus 1/2 mv initial squared. And this F net times d, that's basically the work, the net work, the work done by the net force, the combination of Fa and mg sine theta. So going forward, and I'll show you that in the next video, the work, the net work is equal to the change in kinetic energy. That's a powerful statement. Okay? And the last thing I'm going to talk about is the energy in a spring. Okay. So if I have a spring, and I'm going to stretch it. So when it was not stretched, it was here. Now it stretches by an amount xo, or xo, that's fine. Okay? Now, in order to get it to stretch, some work had to be done. So the work done, and I showed you this in the last video, is 1/2 k xo squared. Okay? Now, if with the spring in this position here, I decide, you know what? I'm going to stretch it even more from here. Now, from this position, from the very top, let's just call that x. Okay? So the energy that it has down here with respect to the unstretched shape is W, I guess I call WO, and this is W equals 1/2 kx squared. Now, if you want to figure out the work done to stretch it, just this amount here, right? Just this. That's got to be the difference in the work is going to be the difference in the energy that it has, right? So the work done is going to change its amount of energy. And this quantity here is what we call the energy stored in a spring, or elastic potential energy. Because when you stretch a bow and arrow, the potential is there of doing some work. And I think that's it for this video. All right, see you later. All right, I'm out. Peace.